Good afternoon, everyone. Welcome to our 1 o'clock briefing today, preparing for extreme weather and flood damage of the 21st century. We have 3 speakers on our briefing today. They are David Neelin, Professor of Atmospheric and Oceanic Sciences at the University of California, Los Angeles; Marika Holland, Senior Scientist at the Climate and Global Dynamics Laboratory at the National Center for Atmospheric Research in Boulder, Colorado; and Marty Ralph, Director for the Center of Western Weather and Water Extremes at Scripps Institution of Oceanography. So we'll hear brief remarks from each of our speakers, and then we'll open it up to Q&A. Thank you.
Thanks. Can you hear me all right? We build our infrastructure around the probabilities of extreme rain event. For instance, you want it to be able to handle the 1 in a 100-year event. Global climate models project that in a warmer world, the probability of exceeding a given size of event is going to increase over most of the globe. These models simulate the evolution of weather systems in detail over the entire planet, over the historical period, and over the coming century with scenarios for the increases of greenhouse gases. They use millions of grid points over the globe, and they step forward in time by small increments, like 15 minutes or half an hour. And then modeling groups all over the world make the results of their simulations freely available so other scientists can evaluate just how well they're doing in their simulations compared to current observations. It's not at all obvious in advance that the models will be accurate in simulating probabilities of precipitation or what will be the major factors in the changes that arise. Now, despite being limited by computational costs to grid cells around 100 kilometers, which can be a factor in the tropics where you have a lot of small-scale cloud circulations, it turns out the models are reasonably good at simulating the probabilities of large events relative to the probabilities of medium events. When we look what causes the change in these probabilities, the standard explanation is, in a warmer climate, the air can hold more water vapor, and so a storm with a given circulation will tend to yield more rain. That would give about a 7% increase per degree of large-scale warming in the size of the events. The statement that more water vapor yields more precipitation is true, but it's only part of the story. In the tropics especially, the low-level air that converges and rises in the storms is condensing into clouds and releasing heat as it does so. That heat derives further circulation, which brings in more moisture and adds to the precipitation you were already going to get. Furthermore, the way the probabilities of precipitation drop off, this effect coordinates with the direct effect of the moisture to particularly enhance the probabilities of the very largest events. The larger the event, the more the probability is going to be enhanced in a warmer climate.
Good afternoon, everyone. So I'm Marika Holland. I'm a scientist at the National Center for Atmospheric Research, and I'm going to share with you some information about the changes happening in the Arctic water cycle. So the Arctic is a frozen place. That's one of its defining characteristics, and that makes it unique in terms of how water moves through the Arctic environment. And the ice that occurs in the Arctic occurs across the system. So we have vast areas of frozen soils. We have vast sea ice covering the Arctic Ocean, snow cover on the land, etc. And in response to human activity, the climate is warming. That warming is being amplified in the Arctic, and the Arctic is melting. And this is causing changes across the entire water system in the Arctic. So during the last 40 years, we've observed a decline in sea ice, a thawing of permafrost, a decrease in the snow-covered area over the land and over the sea ice, an increase in river runoff, and a freshening of the Arctic Ocean. So we're seeing this whole-scale change happening in the Arctic water cycle. And there are strong suggestions that these changes are all interrelated and they're all associated with the warming of the globe. Projections from our climate models indicate that we will see continued and larger increases and changes occurring into the future. So by the end of the 21st century, projected changes will be very extreme and result in a fundamentally different Arctic state. However, the Arctic is also home to very large natural variability. So the same factors that amplify the global warming in the Arctic also cause an amplification of the natural variations in the system. And because of this, for a number of aspects of the Arctic freshwater system, such as changing precipitation, we have yet to see a clear climate change signal emerge, because that natural variability is just so large that it's hard to tease out this signal from the noise. So instead, our model simulations suggest that this signal of a changing water cycle will emerge across the Arctic system within the next several decades, and that by the end of the 21st century, under a business as usual type emission scenario, burning of fossil fuels, we will see an Arctic water cycle that is outside the envelope of the variations that we've seen in the last 100 years, and likely much, much longer. So this will be a vastly different state. So notably, studies using climate models also suggest that these Arctic changes can happen abruptly. So when we have this natural variability that's very large, on top of this forced signal due to rising greenhouse gases in the atmosphere, when the two of those are reinforcing, the changes can be very extreme and rapid. So for example, sea ice exhibits decadal scale rapid ice loss events. And because of the coupling across the system, there's reductions in sea ice cover that can be very large on decadal timescales, also impact things like precipitation in the Arctic. So very rapid sea ice loss, leading to very large increases in evaporation from the Arctic Ocean, leading to very large precipitation increases. So as we look into the future, we expect to see dramatic changes occurring across the Arctic water cycle and a transition away from this cryospherically dominated icy state. Additionally, it's likely that these changes will not occur gradually, that they will be punctuated by these very rapid instances of sea ice loss, precipitation increases, river runoff increases. And so we expect that there will be surprises associated with that as we have these rapid changes occurring across the system. Thanks.
Hi, Marty Ralph from Scripps Oceanography. We're working on a phenomenon that really dominates the global water cycle in the middle latitudes, and it's a phenomenon called atmospheric rivers. We've learned about it over the last decade or so. And for example, in the western U.S., about a third to half of our water supply comes from a few big storms each year, and most of those, if not all of them, are atmospheric river-type storms. We now know how to identify a storm as an AR or not. We also know that they produce most of the flooding. In fact, a very recent paper in AAAS's Science Advances journal in December, led by Tom Corningham, calculated that about 80% of all western U.S. flood damages over the last 40 years were from atmospheric rivers-type storms. And in fact, we've developed a scale that I led the development of last year as well, AR 1, 2, 3, 4, 5. It's essentially the analog to the hurricane scale, but designed around the western AR problem. And unlike the hurricane scale, it has two parameters that determine what the ranking is, both the maximum intensity of the atmospheric river as it passes over a location, and also how long the AR, as we call it, lasted at that site. This is an issue in the hurricane problem for things like events like Harvey and Florence, where the impacts are very disproportionate because they stalled over a location. When an AR stalls, it can deliver a lot of precipitation over a location for a longer period of time. So our scale basically is 1 and 2s are sort of beneficial because we need a lot of water in the West, or sometimes we don't get enough. 3s are a mix of benefits and hazards. 4s and 5s can be pretty hazardous. And in Tom Corningham's paper, we quantified this, and AR's 1s and 2s are under $1 million of damage on average for each one. AR 3s can be in the millions, AR 4s in the tens of millions, and AR 5s typically in the hundreds of millions. We don't get very many AR 5s. About every couple of years we'll get them on the West Coast. But we now see this scale as potentially helpful in situational awareness for the public and decision makers so that they can recognize more readily when a storm's approaching if it's one to really batten down the hatches for or one to maybe take advantage of the water that it's going to generate. In fact, locally here in Seattle last week, we had an AR3 storm hit, but it hit on top of very wet conditions already, and it created some of the highest river flows seen in a long time in this part of the country, including some serious damage in certain locales. I was just meeting with water managers this week in Seattle and Portland, and they both remarked how, for example, the forecast a couple days ahead said a particular watershed was going to get hit worse, but actually the one that got hit hardest was about 100 miles away. And then the one that was supposed to hit after that was similarly in the wrong watershed. Those are the kind of problems we're working on the weather side to try to improve the forecasts of those. One of the key things we got to do is get the AR position right when it hits shore, like a day or 2 or 3 ahead or even longer. One thing we're doing right now, in fact, as we speak, is we're using the nation's Hurricane Hunter research aircraft to fly into the storms over the Pacific where there's not enough measurements of the details of the AR ahead of time for the weather models to predict them properly. And we're adding those measurements in real time into the models, and it's happening literally right as we speak. These sensors are being released by the aircraft, falling through the atmosphere, recording the data, reporting it back, and it's going into the global model. The model that runs at 4 p.m. Pacific time today will have that data in it, and hopefully the forecast of this modest AR to small AR that's aiming for Oregon more will be improved because of it. So this is one of the phenomena that's really key in the western U.S., Western Europe, Western South America, and in the mid-latitudes, these ARs are really responsible they're the drivers of the water cycle. Thank you.
Great, thanks. We'll open it up for Q&A now. If you have a question, please raise your hand. We'll bring a mic to you, and kindly state your name and affiliation before asking your question. Thank you.
Sorry?
Oh, no. Okay. All right. Okay, we have a question in the front row here. Thanks.
Hi, I'm Mary Miller from the Exploratorium. Marty, you mentioned this scale for atmospheric rivers. Is that going to be just advisory? Is that going to be adopted? Because the hurricane scale is something that NOAA uses when they make their predictions. So can you say where you're at with that and how it's going to be rolled out?
The paper was published last year. I'm the lead author, and we have 8 co-authors, 2 of whom are National Weather Service folks. And we at the Center for Western Weather and Water Extremes are developing prototype displays to quantify this in forecast mode and in retrospective, so after an event. Like I could say objectively, this was an AR3 that hit last week. In fact, it was very close to AR4. So we're developing and prototyping those tools, and the National Weather Service staff are in the loop on that and giving us feedback. We're also working with TV broadcast meteorologists who are quite interested in it as well. So it's a process to roll it out, and we want to make sure it's done carefully and that the displays are really optimal for situational awareness enhancement.
Question in the front.
Thank you, Marty. Robin Williams from the ABC in Australia. Where I come from, these storms have become more obvious. And one consequence, dramatically, is that the infrastructure cannot cope. Do you expect to be seeing a similar sort of problem here?
Projections from climate models do show ARs in the western U.S. on average getting a bit larger, and some of them being more intense, partly because, as Dr. Neelin pointed out, the atmosphere can hold more water vapor in these storms. I appreciated his remarks about the tropical systems being amplified even beyond that, and we don't have that diagnosis yet for the mid-latitudes. But it is quite plausible that we will be seeing somewhat larger, longer-lived ARs, and those are the ones that create the big problems for infrastructure.
Question in the back, and then up in the front.
Hi, Mathieu Perrault from La Presse in Montreal. Are there atmospheric rivers in the Atlantic?
Yes, in fact, there's a very active week underway just now in the Atlantic. The UK and France are under the gun, and we looked at that. Although we don't put this stuff out, that was it looks like an AR5 condition would be hitting in France and part of the UK.
Question.
And the eastern U.S. also, I should say, they can curl up across Florida and come into New England and eastern Canada.
How far around the globe can these atmospheric rivers travel? I mean, if you have one here on the US West Coast, can it go right across the continent and across the Atlantic? How persistent are they? How long-lived?
Fantastic question. I've gotten so many questions. I've never had that question. We have a concept of inland penetration of ARs. ARs, the water vapor transport, is down low in the atmosphere, in the lowest few thousand feet is where it's focused. So when it hits the coastal mountains, a lot of it gets rained out. But sometimes it can penetrate inland, in fact, winding its way through gaps in the mountain chains. And there are events that hit all the way into the Colorado Rockies, for example, certainly in Idaho and Arizona and Montana. And then they don't really get all the way across the country. They pretty much peter out over the Rockies. But there are other ARs that can form up over the Gulf of Mexico and move into the eastern U.S. and into the Great Plains. And they also can be the cause of some of the major flooding in that region as well.
Question in the back.
So Mike Dettinger actually scripts also. But I had a question for David. We all hear about El Nino, and when there's an El Nino or La Nina going on, the weather channel goes wild and all that. What are your thoughts about how, with the intensification in the tropics that you mentioned, what are your thoughts about sort of the future of our relationship with El Nino up in in North America, for instance?
Thanks for the question. There are also projections of what happens to El Nino in future climate. Those tend to have a fair uncertainty associated with them, but the hydrological cycle side effects tend to agree. Once you manage to get an El Nino, it tends to have more precipitation rearranged in the Pacific associated with it. One of the main effects for California of an El Nino is a extension of the jet stream towards the U.S. West Coast that tends to deliver more storms with their associated atmospheric rivers onto the coast at the latitude, say, of Southern California, Los Angeles. Under global warming, there is a projection that jet stream extension will occur more of the time, even without an El Nino. So it's an El Nino-like effect that will occur more commonly, delivering more of these atmospheric rivers onto parts of Southern California, for instance, that would not normally get as many.
Question in the front.
Question for Marika. Given the changes in the north around the Arctic, we've already seen a change, as you described, with the jet stream, with the winds coming down. They're slower, they reach further down. Will that result even in an even greater effect on the weather, say, of northern continents such as North America?
Yeah, so that's a very active area of research, I'd say, right now. And there's a lot of uncertainty on how changes happening in the Arctic will affect mid-latitude weather, the weather where most of us live. There are some indications that as the Arctic warms, we see more excursions of Arctic weather into mid-latitudes. But exactly the magnitude, the frequency, those kinds of things are where the uncertainty lies. And so it's very actively being researched, and it's not entirely clear at this point. Yeah. And our models struggle a bit with simulating some of the factors that drive some of these changes. So improvements in the models, more analysis of the observational data is needed to really advance that.
Question from an online viewer.
This question is from Nicolas Luco from El Mercurio in Santiago, Chile. And this question is for Dr. Holland. He asks, could the model of the Arctic process help decision-making in Antarctica?
So the Arctic and the Antarctic are quite different systems in terms of how their icy oceans interact with their atmospheres, but better understanding the processes in the Arctic and how sea ice variability affects the atmosphere above. Those kinds of things are, better understanding of those are things that we can then use to improve and develop our climate models. And that should improve those processes in the Antarctic as well as the Arctic. So, for example, a lot of what we've learned about predictability of sea ice and how predictability of sea ice imparts predictability to the atmosphere above. A lot of those studies have been Arctic focused, but a lot of similar processes, the kind of coupling between the sea ice and the atmosphere also is important in the Antarctic. So we're learning things from the Arctic, some of which we can apply to the Antarctic, but it's not as simple as you'd think because they're quite different climate states.
I know flood insurance is quite complicated, but I was wondering if any of the findings you've published, Marty, have been inspiring conversations among flood insurance policy makers, those who consider such things, the insured loss and damage.
The American Meteorological Society in Boston had their annual meeting this January, and they had some special attention to the economics and investments, and the insurance industry is very interested in this work. What they're doing with it is still not clear to me, but it's clear there's a lot of interest in learning more about how to anticipate these things.
Question in the back, and then we'll come up to the front. Yeah.
Hey, thanks so much. Brad Plumer at the New York Times. Murray, could you say a little bit more about why atmospheric rivers haven't received as much attention up until recently? I mean, were they relatively unknown until recently, or was it just not appreciated?
Yeah, it's a good question. I'd say there was a really critical point about 1998, so crazy that's almost 20 years ago now. New satellite data came on board that showed the water vapor distribution over the oceans in high resolution, and we could see these long ribbons of large water vapor content in the atmosphere, and we could watch them move a bit, and they really were evocative of river-like behavior. And there'd been some studies of relevant phenomena, one called the worm conveyor belt, that was sort of poking around on that. But those images, plus a field experiment I did with aircraft at the time, plus a key paper from MIT, all were 1998. And that really is when the light bulb went off for me, and that's when we started our work on it in earnest.
A question in the front.
Clive Cookson from the Financial Times in London. So I'd just like you to talk a bit more about how one might form, say, in the Pacific that reaches here, or sort of closer to my home, the level 5 event you talked about. Where would that have originated?
They have really two key ingredients. One is dynamics. So the atmosphere is primed to develop an extratropical cyclone where the sea level pressure falls, the winds spin up, and the convergence of temperature gradients and water vapor leads to a strong atmospheric river. The AR's down low where the water vapor is greatest, the air is warmest, and the water vapor is greatest, so it's drawing that warm, moist air in, sometimes from the tropics all the way into the mid-latitudes. That combined with strong winds at about 3,000 feet on average can drive massive amounts of water vapor transport. Now imagine an AR ARs on average are about 500 miles wide and a couple thousand miles long. Slice across one as if you were cutting across a terrestrial river and calculate the water vapor flowing as vapor, not liquid, and the average AR is about 27 times the Mississippi River. A strong AR could be double that. And there's only a couple of 3 or 4 atmospheric rivers at any given time in the northern hemisphere, similarly in the southern hemisphere. And if you add up the water vapor being transported in those 3 or 4 ARs, it's 90 to 95% of all the water vapor transport in the mid-latitudes is happening in these narrow ribbons. So they're genuinely rivers in the sky, but they're water vapor instead of liquid. I don't know if that gets at your question. There's a whole lot of dynamics we could talk about. It's a really good question.
Maybe a question for all of you. Could you talk a little bit about how important ways that models that anticipate future precipitation events, what are some of the important ways that they've improved over time, and what must they still do to get better?
I can speak to the tropical side on that. One factor that's very important for the tropics is just resolution. If you can put more grid points in there in a global climate model, you're going to do a better job of things like tropical storms. And so that'll come with computational capabilities. But another major factor is just being able to understand the processes, because in the tropics, there's such an interaction between the small scale and the large scale that you really need an interaction between field campaigns like the Department of Energy has been putting out. They had one in the Amazon a few years ago, and they periodically have these in the tropics. These are so important for figuring out what are the processes by which the air gets into the overturning thunderstorm cells and how much is coming from which level, and that affects how things change under global warming.
I'd say from the Arctic or the polar perspective more generally, resolution is also key. I mean, I think, that's true probably across the board, that improving resolution in our models, better resolving these very small scale features that affect the atmospheric, moisture transport, et cetera, is very important. And I'd say that we're making big advances in that area. So we're at NCAR, we're a climate modeling center. We develop a climate model. We're pushing that model to higher and higher resolutions, and we're also building capabilities where we can do high resolution in certain areas of the globe that are of particular interest. So because computational power is still an issue, I mean, we run these models on the fastest supercomputers in the world, and it's still an issue. We can't get down to the details that we would really like to get to. But we can now use these capabilities to put, much higher resolution, for example, over the Arctic, the area I study, to better resolve storms there. We can do similar things for the tropics, and so we can start to tease apart these processes and use these new capabilities to better model features in different areas of the globe.
Yeah, I agree. The resolutions have been a big factor in improving precipitation forecasts from climate models to weather models. Also getting initial conditions, I can speak more to the weather model side of things, which is days to a week or so, is getting the initial condition right. So knowing the state of the atmosphere at the beginning time when you run a model is really vital. And we have a lot more measurements nowadays, and satellite data are really key to that. Ocean conditions are really vital as well. And we have global drifter programs now. We have global submersible buoys programs, and our atmospheric river reconnaissance program is an example of a tailored thing. So getting better measurements has been a really key part of it. An interesting factor, though, that I believe is where some of the future work needs to be done, is to get the microphysics right. In other words, how you take water vapor in the air and turn it into a cloud drop. How many times do you see clouds out there and there's no water coming out, no rain coming out of them, right? They're just up there being fine as clouds. Something magic sort of happens to turn that into rain or snow, and that magic is extremely complex. Part of it is that dust particles in the atmosphere are small, aerosols we call them, can trigger the transformation of a cloud droplet, cluster of cloud drops into a single big enough drop to fall out and form rain. And that creates a cascade effect of, I never realized the pun there, a cascade effect of growing many cloud particles into drops. Our models currently do not represent very well the aerosol distribution in the atmosphere when they start the run of the model. And that's an area of active research as well. And how those aerosols then impact the formation of the clouds is itself quite complex. Some aerosols really don't attract water. Others are very hygroscopic, they're called. They really attract water to form on them, and they can help this process very efficiently.
Question in the front. And then we'll have one over here.
Marty, a phrase you used just now, rivers in the sky. That was the title of an article in the New Scientist about 3 months ago. I know it's outside your precinct, perhaps, but that was referring to, in the article, forests and the way water vapor comes up in gigantic amounts, creating a local river in the sky. And when you cut down those forests, drastic effects. Are you studying any of that?
I'm not personally studying it, but I know the evapotranspiration is the technical term for that, how plants then take the soil, water in the soil, and turn it into vapor, part of their life cycle. That if we don't have that evapotranspiration happening in the right ways in the models, we're not going to get the water vapor distribution in the atmosphere right. And certainly wherever that's happening and the wind is converging that and moving it along, it's going to contribute to the precipitation.
Hi, Brett Walton with Circle of Blue. For atmospheric rivers, is there any seasonal forecasting like there is with decadal shifts with El Nino, La Nina, even for as basic as active or inactive for atmospheric?
That's a very active area of research right now, and I'll highlight a couple little things. One is that when we look at Northern California, variation in annual precipitation over a century, from year to year, if you take the 5% wettest days out of the data set and look at how the normal storms vary from year to year, there's almost no variation. The run-of-the-mill storms are almost a guarantee every year in Northern California. By the way, the lead author on this paper, key author Mike Dettinger, is here in the audience. So correct me if I'm wrong, Mike. That the regular storms, we sort of get them all the time. It's the big storms that come and go from one year to the next. And if we don't, and those are ARs in this part of the world. If we don't get enough ARs, we descend into drought. If we get too many, it can create flooding problems. So that really implies that to get the seasonal forecast right for annual precipitation, we need to get the ARs right. We're just really starting down the path of trying to figure that out. We're looking at, and my center's developing what we call week 2 and week 3 AR outlooks. And we've got some promising early signs of signal there, depending on the tropical conditions. For example, something called the Madden-Julian oscillation. If it's strong and in the right part of the Indian Ocean, that can set up a period of greater predictability, maybe even out to week 5 or 6. So it's a very active and important area of research. We work a lot with water managers who are very interested in having any advantage as they make tough decisions going into their annual cycle of water allocations.
Question in the back.
Hi, Zeke from University of Missouri. I guess this is a question for the whole panel, but Marika, you had talked about how these models are very computationally expensive, and I was just wondering, how long do these models take typically to be usable? And in the future, as you add more complexity to these models for weather predictions, do you see them reaching a point where it's just takes so long it's unusable, or will there be some leeway there?
Well, I think it depends on, so weather forecasting, is the model runs are much shorter. In the climate community, we want to run our models for hundreds of years, and we also want to run them with what we call large ensembles, many, many different simulations, and that allows us to tease out the natural variability and the impact of natural variability on the system versus anthropogenically forced changes on the system. We typically will run our climate models for thousands of years. And because of that, we need fairly coarse resolution. So our model resolution is typically about 100 kilometer on a side, our grid cells. So we kind of break up the world into individual boxes, cells, squares, and those are quite coarse. So a model like that, though, we can run 100 years of simulation, the fully coupled Earth systems, so atmosphere, ocean, land, sea ice, biogeochemistry, so a full carbon cycle. We can run 100 years in a week's time, say. But we want, of course, to run with higher resolution. And so we're starting to run our models with 10-kilometer grid cells. And that vastly increases the computational expense. So there's always this trade-off in the climate community between number of years of simulation, number of ensemble members, and how finely resolved you can model the globe. And then, as you said, we're adding complexity all the time. We're adding ice sheets into these models. We're adding more biogeochemical processes into the models, and those increase the expense. So there's always a trade-off, and we're trying to kind of meet as many scientific needs as possible with these models.
And I could chain on to that briefly just to say that in the tropics, ideally you'd like to get down to a couple of kilometer grid size in order to be able to resolve the deep convective thunderstorm type clouds, at least partially. And there are activities that are trying to do that. For instance, at the Max Planck Institute for Meteorology in Hamburg. But those are not going to be running long climate runs anytime soon. So there's quite a strong trade-off between the resolution and the length of the simulation. And the other thing is we've been emphasizing resolution, which is great, but you have to revise the way you represent things that are smaller than the resolution every time you change the resolution. So even if you're running with a kilometer, you still have all the microphysical processes in the clouds that Marty alluded to that are still going to be subgrid scale, and you have to treat those differently for a very small grid than for a larger grid.
I don't see a day when computing has reached the point where it's allowed us to answer all these questions. This field is going to continue to push the envelope of computing and require more and more as time goes by. And because of that work, as that computing becomes available, there will be better and better information on the weather timescale, on the climate timescales. Ocean, atmosphere, land, biogeochemistry, all is just so complex and so interrelated. I just don't see a day when the computing's going to have solved it.
A question in the back and then in the front? Okay. Here we go, right here. Thanks, Andrea.
Marty, could you explain the relationship between the jet stream and atmospheric rivers, please?
The jet stream is what we often fly in when we're doing commercial flights across country or over the ocean. It's up at 30, 40,000 feet typically, and it can be winds as high as 200 miles an hour sometimes. But that air, if you might ever notice or see it on your seat back cover or whatever, that it's maybe 60 degrees below zero or something up there, cold air can't hold very much water vapor. Less than 1% of the water vapor transport in an atmospheric river storm is happening at those altitudes because the air is so dry, even though it's moving so fast. Where the atmospheric river is down low, where the winds might be 50, even 100 miles per hour in a rare case, normally 50 miles an hour, but it's got 10 to 50 times the amount of water vapor in it. So it's moving so much more water vapor along. So literally, the jet stream is way aloft. It's really important for driving the cyclone development that ARs are somewhat related to. But the jet stream is not doing much of the water vapor movement at all. That's happening in the AR down low.
If I could chain on to that particularly for the El Nino application, you may be used to hearing things discussed in terms of low pressure systems and cold fronts, and those are still there. They're being essentially steered by the jet level because these have a deep part to themselves that is being carried by the jet stream, even though it's 10 kilometers up. The insight from the atmospheric rivers is that the cold fronts basically trail an atmospheric river of water vapor transport behind them, and the water vapor transport is what you care about if you care about precipitation. So focusing, now that we have the satellites to see the transport itself, that's a great part of the storm to focus on. It's the most important for the applications.
Good point, and thanks for that. It reminds me that we now have a paper out last year that shows that on average, for a mature cyclone, the atmospheric river is 1,000 kilometers away from the center of the low. And in meteorology, a lot of the studies and forecasts and all that have focused on the center of the low. But only about half of extratropical cyclones have an atmospheric river with them. And 10 or 20% of all atmospheric rivers have no cyclone within any reasonable distance. They're associated with high pressure systems in an unusual way. So they're interrelated, but they're somewhat independent as well. And very recent results are the stronger the atmospheric river is, the more it's able to feed water vapor into a developing cyclone. And that water vapor can release latent heat that amplifies the development of the cyclone further. So there's this is an interesting line of work that's underway right now. Are you a meteorologist by any chance? You're asking great questions.
So this is a broad question, maybe for all three, but it is just, okay, you've been talking about resolution of models and forecasting and projections. Marty raised an issue of aerosols, and basically they're not in the forecast models right now, and yet we believe they play an important role. I would imagine that in each of your fields, there are things that simply aren't in the models yet, and so greater resolution, you're not necessarily going to pick them up, but that are another step towards improving projections, forecasts, usefulness?
So, I'm primarily a sea ice scientist, so I think a lot about the cryosphere and the icy part of our planet. So ice sheets, the vast ice that's over the Antarctic and the Greenland continent, is not well represented in our models. And there are things that are completely missing, like how ice shelves, these floating ice shelves that extend off the ice sheets, how they interact with the ocean. They aren't even represented in our climate models. And there are huge societal implications associated with whether those ice shelves are lost and how rapidly ice can be discharged into the oceans from these large ice sheets, because it has an important effect on sea level rise. So, which of course affects an enormous number of people. So those are the kinds of questions that I think about a lot, are how we better represent those kind of ice processes. I mean, there's a lot of different things we're missing in these climate models, but yeah, that's one.
Can I just amplify on that for a second, David? And it's a question, because I'm not a specialist in this, but I've had this picture in my mind that the ice shelves, they're sort of stuck on the bottom of the ocean, and they're holding back more ice from flowing into the ocean from the land, such that if you remove that ice shelf, it like unblocks the flow of more ice into the ocean, not just the melting of that ice shelf itself, but it opens the door for more. Is that fair?
Yes, that's fair. That's exactly how it works. And the ice shelves, even in some locations, they sit on these pinning points. So there's sort of these topographic features in the ocean that they're sort of stuck on. So
Like
if
a
they
mountain ridge underwater?
Exactly. So if they melt back from there, then they buttress the inland ice. And so if they melt back from there, then the ice can flow more quickly into the ocean. So it's like, removing a cork and there it goes. So there's huge concerns about that, especially in some outlet glaciers in Antarctica. And there's a huge field campaign going on to try and better understand the processes so that we can represent them in our climate models. So.
And just a little blurb for the tropics, freezing processes. You wouldn't think that freezing would be important in the tropics, but all those deep clouds get up above freezing level. Freezing level is about 5 kilometers. And when the raindrops start to freeze or create ice crystals, it changes the amount of heat release that's going into the upper levels of the atmosphere. At the moment, the models are basically saying, it's below freezing, we should start to freeze now. But it's, in fact, depends on seeding of ice crystals from above. You can't really begin to freeze until you get a crystal going. Those processes are not at all well represented. So the freezing as you go up in the clouds is important for rain.
Question here.
Hi, I'm Julia Köppe from Der Spiegel in Germany. I have a question maybe to all of you. So in Germany, we have a quite big group doubting the climate change, and you can be sure whenever you write anything about the topic, you will get thousands of emails claiming, come on, don't lie about that, look at the data. The Earth used to be much warmer in the past. Do you make a similar experience, and how do you tackle this?
I think for me, the short answer is yes. I give public lectures and things like that, and this is something that you hear pretty frequently. I think the evidence is overwhelming, and it's so comprehensive, the changes that we're seeing in the climate. I mean, it's not just happening in the atmosphere or the ice or the ocean. It's happening across the board. So, we're seeing changes in glaciers, changes in ice sheets, a warming of the ocean. So the fact that it is so system-wide, I think, is very strong evidence that there's this underlying cause. It's not just that the ocean is losing heat to the atmosphere or something like that. And then I think the physics that underlies this is very well-founded. This is not new science. The fact that greenhouse gases in the atmosphere lead to a warming of the globe is something that we have understood for over 100 years. There's not, that physics is very well established. So the scientific basis for this is very strong. So those are the kinds of responses I give when I hear this. But yeah, and there's many other things you can point to that make it, I mean, we can look at the chemical composition of the greenhouse gases in the atmosphere and know that they come from the burning of fossil fuels. There's, you know, so there's many different things that you can point to that make it clear that human activity is driving these large-scale changes.
And I could add to that, back when I was a graduate student in the early 1980s, my PhD advisor, who's now fairly famous, told me, you should work on something else. Global warming is a solved problem. So I went away and worked on El Nino for a while. And the reason he said it was a solved problem is because at the global level, you increase the greenhouse gases, you change the energy budget of the atmosphere. It's really simple. The reason it's complicated now is because people want to know, is the precipitation going to change in this season, in this specific place, and by exactly how much? Those are harder problems. Those are the ones we're now working on, not is the climate getting warmer because of greenhouse gases. That's sort of baked in. But when I teach this to undergraduate students, you can do it in a politics neutral way and sort of take the discussion as it comes up and sort of go through, all right, here's what we know, why we know it, here's the evidence, here's what the climate models do, warts and all, here's what they have problems with, here's what they're good at, here's what's simple, here's what's got more feedbacks going on in it, and walk it through that way. But that doesn't translate too well to Twitter.
A couple of additional thoughts. One is we wouldn't be sitting here today if the greenhouse effect didn't exist, because the planet would be ice cold and life wouldn't likely be around. So we don't have warm enough temperatures otherwise. But I think there's more of a socio-political thing going on here, where in science, it's just baked into us that we always challenge previous assumptions. And sometimes in challenging them, we discover something new. Now, that something new doesn't necessarily upset the fundamentals of the broader aspects of those earlier findings, but refines them and makes them more precise. So we are in the business of doubt. We doubt past results enough that we want to make better measurements, we want to make better models, we want to understand them theoretically. And that is fundamental to the progress of science for centuries. Peer review is key to that. However, if one's not involved in science, it's pretty straightforward to portray science as not really knowing the answer, because we're always expressing doubt about the previous findings. And there's even, of course, the problem with smoking in the past and the merchants of doubt who played on that for decades to the price of how many lives, who knows. I fear that's part of the dynamic today, is that the inherent nature of scientists to doubt previous results is inappropriately portrayed or interpreted as we don't know what we're doing, and the earlier results on climate change are invalid.
Last question, Marty, do you have enough pilots signing up to be hunters in your recon missions, or do you need more?
It is a very cool thing, and we tried using a big unmanned aircraft thing to do this in the past, and it's really not up to the task. Manned aircraft, or people, they're really effective, and people are amazingly good at it. So we're very lucky to have folks who like to do that and are well trained in it. If I could add one thing real quick to sort of just a concept that comes to mind as I think about our panel here, and thank Mike Dettinger for organizing our panel, and for AAAS for selecting this for a press conference, and for everybody here who's joined in, is that I guess the way I see it, and maybe I'm just looking at the world through atmospheric river glasses, but I see an atmospheric river runs through it. We're talking, Dr. Neelin, about the tropics and how the details there matter in setting the pattern of storms in the mid-latitudes, and even referred to their impact on atmospheric rivers. So what's happening in the tropics matters to atmospheric rivers. It influences atmospheric rivers. In fact, some ARs literally tap directly water vapor in the tropics and move it poleward. Something we haven't talked about is a very recent paper by Nash et al., just last year, I believe, and we calculated that if you take, say, the 60 degrees north latitude, imagine the Earth with that circle, and calculate the water vapor flux through that curtain that separates 60 degrees north from the pole, that the transport of water vapor through that, half of it is happening in atmospheric rivers. And that half is, 90% of that half is happening in the North Atlantic and the North Pacific. So we are literally seeing atmospheric rivers driving water vapor into the Arctic. And as the Arctic warms, some of that warming is because the atmosphere is carrying more water vapor. Well, where's that water vapor coming from? Some of it is inevitably coming from these ARs in the mid-latitudes. So, in my mind, in my world, an atmospheric river runs through it, all the way from the tropics through the mid-latitudes into the poles.
Just where that ends up going is that water vapor is the largest greenhouse gas in the atmosphere. And so as the atmospheric rivers are pumping water into the polar region, into the Arctic, a lot of the warming and a lot of the problems that Marika was talking about are being I don't want to say, oh, they're being fed by the atmospheric rivers, but that becomes the connection for a lot of what Marika was talking about.
Thank you. Thank you all to all of our speakers. That was an extremely interesting discussion. Really appreciate your time. Now we'll get ready for our next briefing. Thank you.
Thank you.
Thank you.